In this video, we are going to demonstrate an end-to-end external aerodynamic simulation on an electric vertical takeoff and landing aircraft using the Flexcompute Flow360 API. We'll start from geometry, set up the mesh, define the solver settings, choose outputs, and then launch the case. As we do this in Python, I'll also show how everything we define here appears automatically in the Flow360 WebUI, so you can track and inspect the run visually at any time. Let's start at the top of the script. First, we will import Flow360. This gives us access to Flow360's project creation, meshing, solver, and output controls directly from Python. Next, we create a new project directly from a geometry file. This line uploads the geometry, creates a new project in your Flow360 workspace, assigns the project name, and defines meters as the base unit system. Alternatively, if you already have a project in the cloud, you can reconnect to it instead of uploading a geometry again. That's what this commented line is for. Now we create a reference to the geometry inside the project. This gives us access to the geometry so we can group faces, select surfaces, apply boundary conditions, and define outputs later in the workflow. Next, we define the output fields we want to export. These lists simply define what data Flow360 will compute and write out after the simulation. Keeping these at the top of the script makes it easy to reuse or standardize outputs across multiple cases. Now we group geometry faces using metadata from the CAD file. This organizes surfaces based on a face ID tag, which makes it easier to target specific regions later for boundary conditions, refinements, or output extraction. You'll see these groupings reflected in the WebUI geometry tree as well. Next, we enter an SI unit context. This ensures that all dimensional values inside this block are interpreted consistently in SI units. It's a simple way to avoid unit mistakes when specifying operating condition, surface, and volume mesh settings. However, you can still overwrite settings with another unit if you want. Now, for creating the Farfield region, we'll use Flow360's automated Farfield option, which determines and creates the appropriate Farfield dimensions based on the geometry. If you have your own Farfield geometry, then you can use the user-defined option. No changes are needed for this model, since the Farfield is automatically created at 100 times the model's maximum dimension. Now we define the main simulation parameters. This is the Python equivalent of the setup panels in the WebUI. Everything related to meshing, physics, solver settings, and outputs lives inside this structure. Starting with meshing, Flow360 uses an automated meshing process that reduces the amount of input required for the user by providing default values that are sufficient to generate a high-quality mesh for most cases. As you can see here, we only have to provide a surface max edge length and first layer boundary layer thickness. Advanced parameters are available, but not needed for this model as the default values will create a high-quality mesh. Next, we will define a refinement region around the aircraft, which helps resolve flow features in the near field and wake. We will specify the refinement region to be a box, then provide the name, axis, and angle of rotation, center, and size. The Python script can also be launched in draft-only mode, which will help you visualize the refinement box in the WebUI as well to verify its placement. Next, we will specify reference geometry values, which will be used for non-dimensionalizing lift, drag, and other forces and moments to get the force and moment coefficients. Next, we define the operating conditions. This sets the free stream speed and angle of attack for the simulation. One advantage of the Python API is that sweeping over angle of attack or speed becomes straightforward to automate. We then configure steady time stepping. This sets a steady-state solution with adaptive CFL control. For unsteady problems, this is where you would switch to a time-accurate formulation. Now we define the physics models. First, we apply wall boundary conditions to all geometry surfaces. Then we apply a free stream condition to the Farfield. Next, we configure the flow solver and turbulence model. Here we explicitly set solver settings related to Navier-Stokes, turbulence and transition model, and their advanced parameters. You can rely on defaults or fine-tune these settings for more challenging flow regimes. Now we define outputs. This tells Flow360 what data to save and in what format. In this case, we export both volume and surface data in TechPlot format. Additional outputs like slices, monitors, or streamlines can be added here as well. Finally, we launch the full workflow, which sends the simulation to Flexcompute's own GPU cluster, powered by the latest high-performance GPUs. The job is instantly picked up and assigned to the optimal quantity of GPUs based on the size of the mesh. While the case is running, you can open the WebUI and watch everything progress in real time. The project tree updates as each stage completes, just as if you had launched the run directly from the browser. So whether you use Python or the WebUI, you're working with the same solver, the same infrastructure, and the same project environment. The Python API simply gives you a more scalable and reproducible way to drive the workflow. Thanks for watching, and if you would like to take a deeper look at the full set of capabilities, including advanced workflows and examples, we recommend checking out the Flow360 Python API documentation on our website.